Okay, welcome everyone to our final lecture in this course. The next lecture we will be hearing about the presentations of your project. So this is lecture number 13. Before we get started, does anyone have questions or comments? All right, so if not, then let's start with our topics today. We are not going to study um, um, fundamentally new ideas today, except the last part where we might just skim over um, um, model predictive control, which is one widely used control technique. So we might just go over it very quickly. So today I just want to plug the missing link between continuous and discrete time systems. And that's something we should have done earlier, but just for the sake of completeness, let's look at the link between continuous and discrete time control systems. So basically what I mean to say is if you have a continuous time system, how do you discretize it? In other words, how will the system matrices be affected as a result of this discretization process? So if this is the system at hand, and you want to get to a discrete system, which is described as xk plus 1 equals some, so this is like a new matrix now. It will be like A discrete, right? And then B discrete. So we mentioned this before, but we haven't seen the relationship between these matrices. So all these A, B, C, and D will be different matrices. So we're going to start to derive this this conversion, and let's start with the continuous time system. So suppose that a continuous time system has a state space. Again, the same one, x dot t equals a x of t plus b u of t, and y equals cx of t plus du of t. So basically, when we discretize the system, we try to sample it in some way. So if the system is described as follows and it is sampled at some discrete time intervals, of duration capital T, oops, So let's say we have discrete time steps of duration capital T, then a discrete time version of the system will be simply so let me just write it here. It will be x dot or in other words, we will not have a dot here now. We will have like x k plus 1 times capital T equals some some g of t x of kt. And by the way, when we say here in a discrete time model, basically k implicitly refers to k times capital T, where t is the sampling time. Okay, so if you have a discrete time version, after the sampling, we will get something like this. So it will be xk plus 1 equals something, which is a function of this sampling time, times x of kt plus again the h of capital T u of kt. And similarly, the output y will be y of kt equals c x kt plus d u kt. So interestingly, the c and d are not affected as part of the discretization process, right? So C and D are not affected. And the reason why they are not affected, can somebody make a wild guess? So intuitively, the idea is there is a state evolution according to a differential equation, right? So when we discretize the differential equation to a difference equation, you tend to have the different elements here. So the G and the H will be depending on the sampling time because there's an evolution of time. But if you just discretize the output equation, there is no dynamics here, right? So there's no evolution. Everything is a function of the time instant t. So if you were to discretize it, you will simply have like a k times capital T here. Okay. And also the other important thing to note is that the G and H are constant matrices depending on the sampling interval capital T. So there is no time dependence here. They are simply constant matrices. So okay, now if the continuous time system is eventually converted to a discrete time system as follows, then let's start by solving the continuous time system first, and then trying to compare it with the discrete time system. So so we will start with the solution of the continuous time system. Right, so if you go back to lecture number 1, if we had a continuous time system, its solution is composed of two parts. So one is depending on the initial state. Solution looks like e to the power at x of 0, right? The initial condition plus e to the power at, and then you had an integral 0 to t e to the power minus a tau b u of tau d tau. Right, that was the solution to a linear constant coefficient equation, constant coefficient differential equation. So, I mean, in this solution, let's substitute t equals to k plus 1 times capital T, and and t equals to kt. Right, we'll substitute both of these. So, I mean, this is number 1, this is number 2. So if you substitute k plus 1 t, then what you get is x at k plus 1 t equals e to the power a k plus 1 t x at 0 plus e to the power a times k plus 1. Oops, I made a mistake here. So this should be a capital T. And then the integral 0 to k plus 1 capital T e to the power minus a tau b u of tau d tau. And similarly, if we substitute x or t equals to k times t, so we get x at kt equals to e to the power a kt x of 0 plus e to the power a k capital T 0 to k capital T minus a tau b u of tau d tau. Now we can multiply multiply the second equation by e to the power a t capital. So you will get e to the power a capital T x of kt equals e to the power a k plus 1 t x of 0 plus e to the power a k plus 1 capital T 0 to k capital T b u of tau d tau. Okay, so let's substitute this thing here. So this thing appears in the first equation. So substitute in 1, right? So first let's write down what this expression is. So it turns out to be e to the power a k plus 1 capital T x0 equals e a t x k capital T minus e a k plus 1 capital T 0 to k t e minus a tau b u tau d tau. So we need to substitute this in 1. If we substitute this in 1, basically the x of 0 term will be replaced. So we are left with x of k plus 1 capital T equals e to the power a t x of k capital T minus e a k plus 1 t 0 to k capital T e minus a tau b u tau d tau plus e raised to power a k plus 1 d integral e to the power minus a tau b u tau d tau. So now we have the combination of these two equations. So if we simplify, we will get e to the power 80 x k capital T plus e a k plus 1 t. Let's take this common. So you will have 0 to k t a tau b u of tau, and then you will have so we this should be k plus 1, right? So k plus 1 t, and then you have a negative sign. So the other one is 0 to k capital T e a tau b u of tau d tau. Okay, so I mean, this can be written as, we can now combine the integrals. So let me write down the complete step. So xkt plus e to the power a k plus 1 capital T, and then the integral, because it's a subtraction. So basically it means that it's integrating from kt to k plus 1t. Okay, so we reduce the solution in terms of this expression. So from so now there's the interesting thing. So note that from kt to k plus 1 capital T, u of t is equals to u of kt. Right. So to understand this, basically, if you look at the horizon or the time axis, right, there's a kt and then there's a k plus 1 t. Right. So these are discrete steps. So so the input basically is only changes at discrete intervals. So there's something to be different here, but then it stays, and then next time it will be something else and something else. Right. So during this interval, the ut will be actually u of k t, right? The previous value. So to hold, the value is being held until the next time interval arrives. So that's interesting, which will make the integral easy to solve. So we will have x of k plus 1 capital T equals e to the power a capital T x kt plus e to the power a k plus 1 capital T. And then this is the place where the difference will be. So we have e minus a tau b, and this is u k capital T, right, and d tau. So it's become independent of the tau now. All right, so it basically can go outside. So next step, we are going to bring this inside, and we're going to bring this outside. Okay, so so it's xk plus 1 capital T e a t x of k t plus kt to k plus 1 capital T e raised to power a k plus 1 capital T minus tau, because we brought the term inside and combined it. And outside the d tau, we have b and u of k t. Right, so now we are going to change the variables. So let lambda equals k plus 1 t minus tau. Right, so then d lambda equals k capital T no, so d lambda is simply minus tau, and the tau so when because tau is a variable of integration, when tau equals to kt, basically lambda equals capital T, and when tau equals k plus 1 capital T, then lambda equals 0. So now we can convert the integral. So integral will become xk plus 1 capital T equals e to the power at x k capital T plus capital T to 0 e to the power a lambda d lambda b u of kt. So eventually it becomes e to the power a capital T x of kt plus 0 to t. So I think I made one more mistake here. Since there was a negative sign. Where? Yeah. So there's a negative sign here. So which can be reversed by reversing the integral. So it becomes 0 to capital T and e a lambda d lambda and b u of kt. So now here, from here, if we compare the solution to the discrete time system, basically, so x is a function of so this is the dynamics, right? So it's a dynamical system in a discrete time. So xk plus 1 is some matrix times xk. So here this can be g of capital T, right? And then we have this matrix times so it should be bu. So entirely this should be the matrix ht, right? So this is like saying xk plus 1 equals to g times xk plus h times uk. So we've got the conversion now. So by comparison, we we get the following. So g of capital T is e to the power a capital T, and the h capital T is the integral 0 to capital T e to the power a lambda d lambda, right, and b. So that is the final result for discretizing a continuous time system. Right, so that's the exact same reason why I was saying A and the A-B matrices between continuous time and discrete time are not the same. They are related according to this relationship. Okay, so there's a small anecdote here. I can also mention that. So if A is invertible, then the HT can be further simplified as follows. So HT by definition is the integral 0 to t e to the power a lambda d lambda times b. So if A was invertible, you introduce a imaginary object identity, which can be written as A inverse A, and write e to the power a lambda d lambda b. Right, so remember this is an identity, so it doesn't really matter. But what we're going to do is we'll bring A inverse outside. Inside you will have 0 to t a e to the power a lambda d lambda and then b. Now the reason why we do this is because if there is a derivative that exists inside the integral, it becomes easy to integrate. So note that d over dt or d capital T of e to the power at equals a e to the power at, right? So basically the integral of a e to the power a lambda will be simply e to the power a lambda. So therefore the h capital T is a inverse e to the power a lambda, and then here we put lambda 0 to t, and then we have b outside. So eventually it's going to become a inverse e to the power a t minus identity times b. Right, so only if a is invertible. If it's not, then we can use the integral approach to find the HT. Okay, so let's do a quick example of converting a continuous time system to a discrete time system. Consider a linear system with the following dynamics. So x1 dot equals x2 and x2 dot equals minus x2 plus u and y equals x1. So we want to discretize the system. So first thing is, as always, convert it to a state space representation. So you will have like x1 dot, x2 dot equals to a matrix times x1, x2 plus something u, and then we have y equals some matrix plus du. So d is not here, d is 0. Okay, so the A matrix will be 0, 1, 0, -1. And we have a 0, 1 here and a 1, 0 here. So we've got these matrices. Now the question is find the discrete time representation of the system if it is sampled with an interval of t equals to 1 second. Right, so let's say this t equals to 1. All right, so based on what we just saw in this lecture, the discrete time system has a general form. So let's write that first. So we have xk plus 1, t is implicit. And by the way, t is 1, so it's not going to matter. Xk plus 1 is g of capital T, x of k plus h of t uk, and y of k equals cx of k. All right, so c at least stays the same here. And our results show that that basically g of t by definition was e to the power a capital T, and h of t was 0 to capital T e to the power a lambda d lambda and times b. Okay, so the first thing is, how do we get e to the power at? So and e to the power at is also called the transition matrix. If you recall, and that transition matrix can be written as the Laplace inverse of C times Si minus A inverse times B plus D. Right, and that's let's say it's a small t here. So if I try to do this, basically it's Laplace inverse of so the C matrix is 1, 0, and the Si minus A will be S plus 1, and minus 1, something like this. So the inverse will be 1 over S plus 1 times S plus 1, S, 0, and 1. Right, hopefully I'm doing it correctly. And then the B is 0, 1, and then there's no D here. Okay, so that will turn out to be the Laplace inverse of 1 over s plus 1 times. So this will become 1 and the, okay, so we will have a matrix which is 1 here, I think I'm making a mistake. Yeah, so it's simply 1, right? So if you evaluate this product, I think it's simply 1. Is it? No, I think there's a mistake somewhere. So the matrix C is 1 cross 2. So the result will be what, 1? Oh, I think there's a mistake. It shouldn't be all of this. It's simply SI minus A inverse. That was the transfer function that I just wrote. So SI minus A will be 1 over S plus 1. I forgot what it should be. It was S plus 1, minus 1, 0. So the inverse will be S plus 1, S, 0, 1, right? So it's S plus 1, 1, 0, S. Okay, so it's Laplace inverse of 1 over S. And then 1 over S plus 1 here, 0, 1 over S plus 1. Yeah, okay, so if this is the transition matrix, then it evaluates to 1 e to the power 1 minus e to the power minus t, 0 e to the power minus t. So we've got the g of t, but the t has to be replaced by capital T, which is 1. So let's go to the next page. So therefore, g of t equals this matrix 1, 1 minus e to the power minus t. Let's move this down. So, and the t equals to 1, which will make it 1, 1 minus e inverse, 0 e to the power minus 1. Perfect. So the g of t or the g matrix is there. Now h of t, we can first see if A is invertible or not. So A matrix A is basically 0, 1, 0, minus 1, right? And determinant of A is basically 0. So A is not invertible. Right? So we cannot simply use the nice formula for H matrix. It has to be computed from the first principles. So H of t is 0 to capital T EA lambda d lambda times B. So we already have the e to the power a lambda, which will be 1 minus e minus lambda. So we have to integrate this, and we multiply with b, and b was 0, 1. So it turns out integral of 1 is simply capital T. It will be lambda plus e to the power minus lambda, and we have to put 0 to capital T. This is 0. This is minus e minus lambda times 0, 1. So if you simplify this, becomes capital T, T plus to the power minus T minus 1. This is 0. This is 1 minus e minus capital T. Okay, so if you simplify this, it becomes T plus e minus 1 minus capital T minus 1. Okay, so finally, because T is 1, so we just have e minus 1 and 1 minus e minus 1. So that's it. We've got our discrete time system. Is basically xk plus 1 is equals to 1 minus e minus 1 like this times xk plus e minus 1 uk, and then y of k is simply the c, which is as before, times x of k, and there is no d, so we are done with that aspect. All right, so that was all for the discretization part that we wanted to talk about. And we should have done this earlier, but that was a missing piece, so I just wanted to. But I mentioned, with MATLAB, you could find the A, B, and C, D for discrete equivalent system. But if not, then here's the exact process and procedure. Okay, so now I want to give you a map of what we've been studying in this course, so that you're able to create a diagram in your minds of what are the things that we have talked about, and how do they connect with each other. So generally, we can talk about linear control systems, and they could be either continuous or discrete, right? So that's what we just saw. So one branch is about continuous time, and the other branch is about discrete time. Right, so basically, meaning to say that you're looking at models of this form, or you're looking at k plus 1 situation. So it's a x of k plus b u of k, and the y of k is similarly cx of k plus du of k. So these are kind of broad domains. And in this course, we have really focused mainly on the continuous arm or the left half of this diagram. We started off with looking at the continuous time systems from a controllability standpoint. So we said that they are, either systems could be controllable or they could be uncontrollable, right? So so if they were controllable, basically we went on with the controller design. And if the systems were not controllable, we said, why don't we do a controllable decomposition and then proceed with the controllable design or controller design, right? And in the controller, we again had different options. So one is the open loop control. Right, so in the controller design, we could do an open loop control. Which is when we say open loop, basically the control input u is arbitrary. So you whatever input you provide, you get a corresponding output, right? And based on the output, you try to manually adjust the input until you you arrive at the desired response. That's an open loop sort of a controller design. But we then saw closed loop or feedback control, right? So sometimes we call it closed loop, but also feedback control. So when we say feedback control, the implication is that u equals to minus capital Kx. Okay, so after this closed loop controller design in the form of u equals to minus Kx, we looked at the observability aspects of the system because x may not be known, right? So there is this branch of the system unobservable. So right, but then there were systems which were observable. And we then went on to design feedback. We went on to design observers for them. So, okay, so if the system is controllable and it is observable, then we can proceed. But if it is unobservable, then again, we could have done a decomposition, right? So you could do a so observable decomposition. These are all ideas from the first couple of lectures that we saw in this course, right? So what that means is you split up the system into multiple components, which are composed of states that are observable and states that are unobservable. And then based on the observable states, you will design an observer. So if the system was observable, you could again have two possibilities. One is if X is completely known, right? So if X is known, meaning that that the output Y could be simply X, right? So the X is completely known at the output. So if that's the case, then we proceed with the state feedback control. Right, so this is simply U equals to minus KX, and you go and do techniques like pole placement and so on. The other possibility is that the X is unknown, right? Meaning that the Y is not equal to X. So you may have to do some observation. So here we will have observer design. Okay, so observer design again could be done in different context. So the first context is when system is noisy or the system is not noisy, so no noise. So there's no noise, then you can simply design a Leuenberger observer. If the system has noise, then you have to go to a Kalman filter. Okay. Now looking at the state feedback control, we looked at actually three different types. One is the pole placement. Right, this we do if you already know the desired pole locations. Right, and the pole placement you could have done using canonical form, or you could do using Ackermann formula, right? And on the other hand, we saw something of the type of LQR. Right, so LQR is again can be done using a finite horizon or a infinite horizon. Right, I hope you're making the connections. And in the middle, we also did a third type. So we did a hybrid controller. So with LQR, we also said if you have prescribed poles or pole locations, you could do a mixture of the two. All right, so basically then what you could do is we we combine the observer and state feedback controller in different forms. So if you combine the pole placement and the Leuenberger observer, you will get some controller, which is called the observer-based feedback controller, right? So if you combine this and this, basically you will get observer-based feedback control, right? And on the other hand, if you combine the LQR and the LQR and the Kalman filter, you will get something called the LQG, right? Linear quadratic Gaussian. So to combine this and this to get this LQG, and both these LQG and LQR basically will create a dynamic output feedback controller. Right, so this basically diagram really summarizes what we have been talking about in this course. Okay, I hope, you know, by looking at this, you kind of traverse through all the lectures and the topics that we have been covering in this course, and all the ideas. So this is mainly on feedback control, but before we you know, we wrap up this course and the semester, I really wanted to talk about one more type of controller, and that's also a very practical and widely used controller. It's called an MPC. So let's okay, give me one moment. Yeah, so next, so we will not see a lot of details about it, but there's something called a model predictive control. It's very related to the state space, so I wanted to mention this, but it may be outside the scope of the current class. But hopefully, you know, if in the future you want to use this for your research or your projects, this is something that is very practical and people use it a lot. It's also called MPC, and we are just going to skim through it. I have a few slides that I'm going to show, so hopefully that makes it easier to follow. And remember, the solution of an MPC is not, you cannot do it by hand. So I just want to make use of some slides here to give you an overall picture of what the controller is and what is different, how you could actually use it. So model predictive control, or MPC, also sometimes people refer to as a dynamic matrix control. These are historical names, or a generalized predictive control, or also sometimes receding horizon control. So the core idea here is that you try to numerically solve an optimization problem in each step. And it's a constrained optimization. And typically it is of the form of a quadratic program or a linear program. So I'm not sure if a lot of people are familiar with these words here, but if not, that's okay. At some point, you might run into linear programs and quadratic programs in optimization literature. So if you look at optimization, you will come across these terms a lot. So so basically, in the MPC, there's a optimization problem that you solve at each step of the iteration and then determine the control input. That's the fundamental idea. So the block diagram looks like the following. So you have a horizon which you use for prediction of both the input and the output. What it means is using the current input, you provide that to the plant. The plant will provide you current dynamic system states, and then those are fed to the plant model to get the output. But obviously, those outputs are at the current time. So there's a predictor which will predict what is going to happen if the same output continues. So you will have like a prediction over certain horizon. This prediction is actually used and is fed back to determine the next controller input. So imagine you use an input to provide a prediction of the output, and then you try to minimize your cost function. But based on this, you compute the next input under the constraint that you want to minimize your cost function. So we'll see this in a more mathematical way in the upcoming slides. So the major advantages of an MPC is its formulation is pretty straightforward and using some well understood concepts. You can explicitly provide constraints on the input. That is something we haven't been able to do in our feedback control design. In other words, our controller gains could have been any number. There was no bounds on the controller design or the controller gains, observer gains, everything was unbounded. But if there's explicit constraints on those quantities, then MPC is a very natural way to handle those. But again, this particular topic involves knowledge of optimization, and some of you might not have the background, so we do not deal with that in this course. Now, the fundamental parameters are the prediction horizon and the optimization problem, and these are well understood components. So let's quickly proceed and look at the history of the MPC. As I said, it used to be called dynamic matrix control, and it's coming since the 1970s with many successful industrial applications. But its theory, meaning its stability proofs and so on, are still lagging behind 10 to 20 years. So, we don't have the explicit proofs of many ideas like stability and other concepts, but at least the controller works and is used in many practical applications. So these are some of the emerging different controllers related to the MPC. And the applications could be many. It could find applications in many domains, such as path planning and control. So, for example, if you were to guide a missile from or a cruise missile, once you shoot it up in the air and you want to guide it until it reaches the target, MPC is the most promising approach to do it. So what happens is there's a trajectory that it follows, and at every step of the trajectory, you optimize and readjust your control input. So by doing it iteratively at every time step, you are eventually able to guide it to the exact point that you want. Otherwise, you need a model to compute the controller input and then let it go, and it might not even reach the target. So similarly, other applications like underwater vehicle guidance, spacecraft rendezvous with the space station, right? So things like, for example, if you want to align two things in a dynamic way, it's the MPC is a good approach. Another possibility is like air refueling. When two aircrafts want to refuel, they will actually have to align with each other, and such type of applications can be dealt using MPC controllers. So let's look at the details of how we formulate the control problem and then how do we solve it. So imagine you have a discrete time system of this form, xt plus 1 equals axt plus bu of t. And again, just like our LQR controllers, we could formulate a index or a cost function. And here the cost function is the infinite sum from time t plus 1 to infinity of y of tau squared plus r times u tau minus 1 whole squared. So essentially, this cost function says that you want to minimize the final output value, the squared value of the output, and you also want to minimize the difference between the u's, like two successive u's. So this will mean that you don't want to dramatically increase or decrease your input, control input. And R could be a constant. And again, these are squared. So just to take into account the negativity somewhere, you just simply square the values and construct a function. Now this one is an infinite horizon problem because it goes up all the way to infinity. So you're saying that you want to minimize this aggregated values of this summation, and subject to the constraint that the absolute value of u of tau is less than some u naught. So the control input has some constraints on it. You cannot have a very large value of u, so you've put this bound. Now this piece here is a constrained optimization problem, and basically for people who have never seen problems like this, there are optimization solvers and computational toolboxes that can provide a solution to this for u of t for all time. So, but essentially the MPC problem is to find only the next input. So you just need the input for, even though you can compute it for the longer horizon, but you will act only on a single step. So imagine if that was a problem, and you want to implement it to control an object from a place in this Cartesian plane to the origin. If you place it somewhere, this is the optimal trajectory it's going to follow based on the initial positions, right? So what happens is it has some initial conditions, but the MPC controller successively steers the object to the origin, and this trajectory is controlled by the cost function. Cost function is saying you don't want to dramatically change the direction because u of t minus u of t minus 1 has to be small as possible. So that's why there's a gradual change in the direction, and these blue paths are cost optimal, so they minimize the cost function. Now, there is also the possibility of a finite horizon MPC. So if you reduce this to an n-step problem, the same problem you could write as follows. And the solution to this problem has to come from some solver. So you could use an MPC problem solver to give you the U of t, right, based on the solution of this problem. Once you find the U of t, then the dynamical model will give you the xt plus 1. So you got the xt plus 1 from the dynamical system model based on some optimized u, and when this xt plus 1 arrives, then the next step it becomes x of t. So so from here, basically u of t goes here, and then x of t becomes xt. Right, and then you go back again to the solver, find another u, go back, and so you keep iteratively generating the input u and controlling the system. Okay, so more generally,
sorry, Professor, in the previous slide, it was not like a feedback that we read in our lectures as well. What is the difference? So
yeah, so the difference is that the u is not equals minus kx, right?
Yeah,
so
yes.
u is a coming from the solution to the optimization problem.
Okay, thank you.
Right, so I mean, so there's a state x, right, and u here is a variable. So u of t entire, so u0, u1 to un is a variable in this optimization problem. So if you solve this optimization problem, I mean, you have to use some MPC problem solver. MATLAB already has solvers for linear and quadratic optimizations. If you want, you can check out fmincon in MATLAB. Okay, so once this optimization problem is solved, then you get a u. So this u, obviously you will get a array of u, right? So for example, u of maybe a large array, right? T plus n. So you only use this value, and you input it to the dynamical model. So you generate a new state, xt plus 1. And this xt plus 1 in the next time step becomes the old one. So we keep running this loop and keep generating newer paths. Obviously, all of this would have been more clear if we did an exercise or an implementation in MATLAB. But again, I don't want to push everybody through this exercise, but people who are interested should definitely try this out. So in a more general setting, we can write a predictive system model as follows, where the output y can be written as some linear mapping from the states, from the future control inputs and the current states. So if y is a vector of future outputs, then it depends on the future control inputs and the current input u. So the matrices G and H and F can be written as follows. So somebody has made a compact from this model. You can make it a compact representation and say that the G is these controllability matrix. H can be formulated like this, which is really like the impulse responses. The capital F here is the, again, impulse responses. So it's a more matrix friendly, computer friendly format somebody has come up with. Now in the MPC, assume that control U is applied and the state X is sampled at the same instant T, then the entire sampling interval is available for computing U. So if you look at these two time horizons or time intervals, basically, as I told you, the computations at the previous step are basically part of the current time step T, and we have U of T and X of T at this point. The next time interval, you will get a, based on the X of T, you will compute U of T plus 1 and apply it. And what you need is, for the next cycle, you will need xt plus 1, which you compute from the state space model. So it's just to try to show you that U is the output of the optimization, and X is the input or the computation of the state at both of these time instants. Now, from the compact representation, we saw the MPC problem can be written in the matrix form as follows. So again, to make it computer friendly, because previously this type of cost function is hard to put into the computer. You can put it, but it's you have to use some for loops and make the summation part of the MATLAB implementation. But with the compact representation, you could represent them as matrices. So Y transpose Y, which means like the summation of all the outputs. And this is the inner product. And then R times this complicated representation subject to the entire vector of inputs less than U naught. And again, the prediction model is compacted into this formulation. So this formulation can be directly a quadratic programming problem, right? And there are a lot of efficient solvers to do this optimization. So based on the X, the current state, you solve the MPC or a QP solver, and then you get a U. So as I said, the UT plus 1 is only the immediate. It's U of 1. So we only use immediate or next U. Or let's say one step. Okay. So again, this is a reformulation of the QP, and the core idea is you can use some standard QP codes to solve this problem. Again, for some people, it may seem very abstract, but if you've ever solved an optimization problem, I think this should look very familiar to you. If not, you don't have to worry about it for this course because it's not in the scope of our discussion. Okay, so there are adaptations that people have studied in the MPC to resemble the linear state feedback that we have talked about. And the goal is to come up with references to the linear system that we have talked about, right? So people want to see eigenvalues and other properties. So there are ways to do a linearized version, something called a linear MPC, because generally, as we said, it's a quadratic program because of the cost function. So it's not really a linear system anymore. But again, there are ways to linearize it and express it in a form that is compatible with our LTI analysis. And you could again use poles and zeros and eigenvalues to study the properties of the controller. Here's an example of how an MPC works. So basically, the goal is to control this car and in a lateral way. So you want to turn and also move in a forward direction, right? So for example, this is the lane direction. You may want to do a this type of a trajectory for this vehicle. Now the simplest kinematic model of the car driving at speed v is the following. So this is the state space model, right? I mean, I hope everybody by now understands what is happening here. So x is the this direction, y is this direction. So x evolves as v times cosine of a. A would be the angle, right? A is this, and so the y changes as v sine of a, right? So v is not an input; it's just a car driving at some speed. What you do is simply you change the steering, right? So u is the steering, and steering just changes the angle of that movement. So you simply are trying to steer and steer a car which is moving at a constant velocity. Okay, so let's see how we can do this with the help of an MPC. Now, first thing was the system is a nonlinear system because of the cosine and sine elements here. And what we do, the first step is to linearize it. How do we linearize it? The simplest way is to use approximation. So assuming a is smaller than 1, much smaller than 1, then sine of a is approximately a, and cosine of a is approximately 1. So if you did that, then the discrete time system can be written as the following. So you've reduced your original continuous time system to a discrete time linearized system, right? Because that is where you can use all the control techniques we have learned so far. Okay, so the state space model becomes like this. The state is this. This is our A matrix. This is B. This is C, and there is no D. Now, first thing is to formulate a predictive model. We are using the compact representation, and the MPC objective function turns out to be this. So it is y times y transpose, right? Sorry, y transpose times y plus r times this u, d, d, and u. And we want to minimize this cost function subject to the condition that everything is less than u naught. And we use some quadratic programming solver to do this, and then pick the first, the immediate next input, feed it back to the controller, get the new state, new output, and again do the optimization problem. So here is the solution. So over time, the steering control is what we are doing, right? So this is a key, the input. Basically the main result of the MPC controller. So MPC is telling us that at time 0, don't do anything, and then do -1 degree. So you do 1 degree and then keep at 1 degrees, and then go back a little, and then immediately change it to 1 degree, +1 degree, right? And then +1 degree, and then reduce it, keep reducing, and then successively keep reducing at every step until the angle becomes 0. Right, so you see what is happening. The driver is turning the car and then bringing it back. So it's like, if this is the lane and the car is moving here, right? So you want to do a lane changing maneuver. So basically you turn, your angle becomes, let's say negative. And then at this point, you turn back. So the angle becomes positive. But this is the output of the controller, right? So you see at the end, it does things very gradually. So every time it generates a new input, which is getting smaller and smaller and eventually becomes 0. So at this point, you know, the car has successfully changed its lane, and its input becomes 0. So this specific curve is the controller that we have come up with. This is the result of the MPC, I would say. So in our previous controllers, we simply used u equals to -kx, which is like a static controller, right? Or even though we had a dynamic controller, but that's depending on the controller gains. So controller gains are set, and we let the object or the dynamical system do its job. But this one is like adaptive steering. So you adapt at every time step and making sure that the desired objective is met. So if there is something that happened in the middle, you can still correct it, because this controller will be computed at every time step. So now look at the other measurements. So one is the heading angle. So what happens is the heading was previously 0, right? And then immediately heading angle changed to reduced, became negative to -1.5. So kept becoming negative to, and became -1.5 here. And from here, suddenly it started increasing successively, and then again became 0 here. Right, so you see the heading angle variations. And it's very elegant to see that this is like a linear behavior. So heading angle changed linearly, But as the time passes, we keep reducing in a very linear manner, and again increased in a linear manner until we reached at the end where things have to be tapered off. Similarly, the lateral error, initially we have a huge error, right? Huge error meaning error is here between our current trajectory and the desired trajectory. So that error starts to reduce, and eventually becomes zero as we reach the final. So my point is, in many practical applications, MPC can be very, very useful. So even though we need I mean, dynamic feedback controllers in many applications, but most of the times we are looking for adaptivity. We are looking for the end goal. We don't care much about stability or other things. So something like this can be very useful. But obviously, the feedback control has its robustness. It is backed by a very strong theory, and in applications where you want to do disturbance rejection, you want to do tracking, you want to do stability and a certain type of response, like for example, you want overshoot or you want a damping behavior, all those properties can be enforced by feedback control theory. But where you don't care much about those properties and you really care about the outcome, for example, when we are guiding a missile to its final destination, we really don't care about other things. We really care about the achievement of the target. So in that case, I think MPC is it's a very, very useful tool. And see the control input is computed at each of these dots here, right? And these decision horizons are actually shown here, right? So these are the this is the time step at which the decision or the control input will change. Okay, so probably that was it for the MPC controller. I just wanted to give you overview, and hopefully if people are interested, they will go back to it and read about it, maybe find some implementations in MATLAB. But definitely, if you are into control and if you're into controller design and working with dynamical systems, I would think this is a very useful thing to be familiar with. Okay, so we're almost done with our lecture today. I just wanted to make a few announcements. So first thing is the quiz, right? So we are left with quiz number 6. And as I said, quiz 6 is not going to be from today's lecture. It's not going to be from any specific lecture. It is going to be from the high level concepts of the entire course. Right, so maybe the diagram that we saw this in this lecture, that the mapping can help you, or things like that. So, I mean, I really think everybody should be able to do it. Whoever has attended the lectures and did the homeworks and did all the quizzes, previous ones. So there should be no peculiar thing for you. And I hope, you know, this could boost up your grade for people who have not had a great performance in quizzes earlier. Then the next thing is about the project mid review. So I've given comments to people. A lot of people are on the right track. They are doing pretty well. However, some people have not turned in their mid review. I would highly recommend to turn in your mid review. So the simple reason is that I don't want you to hit the wall when you submit the final report, right? So I mean, if there's something which is totally, it has happened in the past. So there are people who submitted the report on the last day, and it was plagiarized. So they had to suffer significantly in their grades. So I mean, if you're planning to do something last minute and submit a plagiarized report, I would seriously recommend you to reconsider that and submit a mid-review report so that you have a clear picture of where you're standing, and I understand what is coming up. So generally, I would recommend everybody to make sure that the project reports have the clarity in system model, right? If you're considering a system, let's say you're considering a cruise control, you're assuming some sort of a controller or some sort of a system. What I expect is at least the system dynamics are clear. So if there is no dynamics in the system, I wonder how you're going to control it. So at least the system dynamics should be made very clear in the system model section. So make sure the mathematical model, right, or system model, system dynamics are clearly highlighted. Okay, so there are people who have generated results. They have put some simulations, but I don't know what is the system really is. Is it a linear system? Is it a non-linear system? Is it a I mean, I don't know what type of system. So they have to make sure that they clearly highlight the system that they are working with and what type of controller they are designing. Right, so what type, like a feedback controller or a PID controller? People have done different type of controllers. So I would definitely want to see the details up front. Other than that, I think there are people who have not submitted ample information for me to see what their project is. So I would say to resubmit report if you're asked to. Okay, and the final thing is about the project presentations. So the expectation is, last time we had a poll for project presentations. So there are several people who will do Zoom presentations. So I'm going to schedule will be announced for Zoom presentations, right? And Others who have opted to do a recorded presentation, we will try to play the recordings during the lecture if time allows, and if not, we will upload everything to the Canvas folder so everyone can have access. And for the class presentations, you know, the expectation is a 10 minute talk plus so I would say let's do a 10 to 15 minute, including questions. Right, so you could do 12 minutes and 3 minutes for questions, or some combination of this. So I mean, if you're presenting over Zoom, you have up to 15 minutes to wrap up your presentation. And yeah, and then you will have final projects due project reports due April 28 or 29. Let me
28.
Right. And make sure you have so it should be a formal report, right? So make sure a formal report and without the MATLAB codes and other things, right? The report, the document should not have MATLAB codes in the main body. Right, so the code should be separately submitted. Okay, so I guess we will end at that note. I hope this course, you know, was valuable to you. And unfortunately, we didn't have a lot of in-person attendance. Hopefully, starting next semester, after the summer, we will have largely in-person classes. But anyway, I hope you had a lot of fun this course and you learned something new and useful. And I hope to look at your projects and see what have you been able to achieve with all this information. So let's meet next time with your presentations, and then hopefully wrapping up the semester. Okay, so any comments or questions, just feel free to send me an email and we can take it from there. Apart from that, if you need anything, any help outside the course as well, feel free to write to me, and have a wonderful rest of your week.
Professor, will you announce for the people who are doing the reporter presentations when they need to be due and how to submit them to you?
So yeah, I will upload a link for them to submit their presentations. And that has to be before the, has to be Wednesday night, so that we have it available next day. So during the lecture, we want to have access to the presentations. Okay, so along the schedule, I'm going to upload this link for you to submit. And I'm not sure if everybody can because sometimes the videos can be large, so it's up to you the way you want to submit it. You could use Zoom to record it, or YouTube, or whatever, whichever platform you want to use. Feel free and submit the link, or some way to access that presentation. Okay.
And
Okay.
Professor, one more thing. The presentations, are they next week or the week, the 28th, that the projects are due?
No, presentation is next week,
Okay, thank you.
April 14th. No, April 21, sorry. April 14th is today.
Okay, thank you.
Yeah, I mean, the point is you have the presentations, and then you can finalize your reports and get done with the course. Okay, anything else, you feel free to send me an email. All right, see you next Thursday.